So in section 5, we're going to talk about polar equations. We've already looked at some of these in class, and what we're going to investigate in this video are how do we take polar equations, polar curves, and put them into other types of equations that we've also been studying. So the first type we're going to look at is how do we go from polar equations to parametric equations. Remember that from earlier in this chapter. Parametric equations, they have a separate equation for both x and y. So two equations, and they're going to involve a third variable. What we're going to be using to do this is some rules that we've been using since section 4. And they're written right there, and we can take these and we can solve for r. If I were to divide this first one by cosine, I would get r equals x over cosine. And if I were to take the second one and divide by sine, I would get r equals y over sine. So we're going to be using that fact to help us out in the first one. We're going to take the equation r equals 4 cosine of theta. That means I think of the different directions that I want to go. I plug in all these different angles, and whatever I get for r, that's the distance that I'll be going out at the particular angle that I'm looking at. So if we're going to put this into parametric equations, that means I need to end up with two separate equations. So all I do is, first I'm going to take what I know r is. In one form, it's x equals cosine of theta, and I plug it in for the r right there. And so I would get, from that, I would get x over cosine of theta equals 4 times cosine of theta. And then I want to solve for x, so I take that, multiply both sides by cosine. I'm going to get x equals 4 times cosine of theta times another cosine of theta. And that's my equation for x. I do the same thing for y. I go ahead and I take what I know r equals using a y, and I go back to my original. I'm going to plug it in for the r right there. So I get y over sine of theta equals 4 times cosine of theta. And again, my goal is to solve for y, so I multiply both sides by sine this time, and I get y equals 4 times cosine of theta times sine of theta. And so now I have two different equations, one for x, one for y, involving a third variable. In this case it's theta, and I'll show you in class how this original equation really does match up with the parametric equations we just found. In part C, we have two examples, and here we're going to be looking at polar equations and comparing them to what we're used to from all of first semester and most of second semester, rectangular equations, just involving y equals things in terms of x. First thing we're going to do is look at how we convert something from polar to rectangular. We start with r equals 2 times secant of theta, and this one really, we don't do a lot with this. Probably example 2 we do a little bit more with, but basically you want to try and get, you want to somehow use these equations again. This is how we convert back and forth between rectangular and polar. So somehow you're going to use these equations to get r and theta out of the way and just have it in terms of x and y. So I'm sure we don't really know what this thing looks like right now. I'm just going to do a little bit of algebra. I'm going to try and get r and theta on the same side. So I'm going to divide both sides by secant of theta. And so I would get r divided by secant of theta equals 2. And another way of writing that is r times 1 over secant theta equals 2. And if you remember, 1 over secant is the same thing as cosine. So we have r times cosine of theta equals 2. We know that r times cosine of theta really equals x. And so in the end we have the equation x equals 2. It's now in rectangular form, and what that means is that the original that we started with really is just a vertical line at x equals 2. Those are the same exact graphs. I'll show you in class that that is true, but beyond that, don't worry too much about these types of questions. Okay, and then the last one is how do we convert from rectangular to polar? And again, at some point here, we're going to be using these equations that we've been using. We're going to look at a line. Right now, that line is in standard form. But just so you get an idea of what it looks like, I've converted it to slope-intercept form. So it's going to go through the y-axis at -5/3, have a slope of 2/3, just so you get a picture of it. But if we were to take the original and we want to try to convert that into a polar equation, that means that eventually I have r equals something in terms of theta. The first thing that you're going to do is replace x and y with what we know they're equal to, and that is using the equations in the box right now. So instead of 2 times x, I'm going to have 2 times r cosine of theta, and instead of 3y, I'm going to have 3 times r sine of theta, and it's still going to equal 5. So I've just done some substitution. Then when I look at this, remember that you want to solve for r. And when I look at the two parts right here, the only thing they have in common is r. I'm going to factor that out to the front. So I'm going to have r, and then what's left behind in the first chunk? 2 cosine of theta. What's left behind in the second chunk would be a 3 sine of theta, and it's still going to equal 5. Parenthesis there. And then I want to solve for r. How do I do that? I need to get rid of the entire chunk that I'm underlining in red here. I want to get it away from the left side, so if I divide everything by that entire chunk, I'm going to end up with r equals 5 divided by that entire chunk, 2 cosine of theta minus 3 sine theta. And by definition, I now have a polar equation. R equals something in terms of theta. And so again, in class, I will show you that the graph of this weird-looking thing is the same as the graph of this line. That is the end of section 5. We'll talk a little bit more in class.